since the last 2-3 classes we have been discussing 2D NMR. Especially in the last class I discussed about the COSY, a correlated spectroscopy. I mentioned COSY is nothing but a 2-pulse sequence, 90 T1, 90 T2. We have only preparation period, evolution period and detection period. T1 period is the evolution period, and we collect the signal in 2 dimension, do the Fourier transformation, you get a 2-dimensional spectrum. And what does these 2 pulse sequence does? Especially when you consider the spin system, single uncoupled spin, single spin without any coupling to anything, or 2 uncoupled spins or 2 coupled spins, various examples we took. I explained to you, if you consider a molecule like CH-Cl3 with 1 proton, if you ignore the coupling with carbon-13 natural abundance, then we get a single peak. It is only 1 chemical shift. When we take such an example, such a molecule in the COSY pulse sequence evolves in the T1 dimension at the chemical shift of the proton, and at the T2 dimension also, in the T2 dimension evolve with the same chemical shift, and such type will give rise to a peak when you do the Fourier transformation, which comes on the diagonal. And if you go horizontally, you get a frequency which corresponds to chemical shift of proton in the T1 dimension, same CH-Cl3 proton. Come vertically down, you again get the chemical shift of the proton CH-Cl3 in the T2 dimension. So the frequency of this one, which is on the diagonal, remains same in both the dimensions. It does not change. And I took the example of, let us say, 2 uncoupled spins. We get 2 peaks on the diagonal. Each of them correspond to chemical shift in both the dimensions, identical chemical shift of the same spin. If I have 1 proton here CH-Cl3, in both the dimensions it gives the chemical shift of CH-Cl3. If I have another peak on the diagonal, both the dimensions it gives rise to chemical shift of some other molecule. I explained to you about 3 spins, and then I took the example of 2 coupled spins. Interesting thing is 2 coupled spins, 2 AX spin will give rise to 4 peaks, 2 for A and 2 for X. When A spin, when it evolves at its own frequency, that means at its own chemical shift in T1, and during the process after evolution, it gives part of its energy to proton X, which is coupled 2. And then it evolves not only at its frequency and also evolves at the frequency of X. That means when it evolves at its own frequency, it gives a diagonal peak. When it evolves at its frequency of X, it gives a cross peak. Similarly, X will evolve at its own frequency and gives rise to a diagonal peak, and it gives part of its energy to A and evolves at the frequency of A spin, gives rise to cross peak. And I explained to you, when we have 2 coupled spins, we have 4 peaks diagonal in the square pattern for A, 4 for X, and they come in the square pattern, and we also understood they are all autocorrelation peaks. 2 peaks will correlate within themselves, and the cross peaks are correlation of A and X. A gives its magnetization to X, gives rise to cross peak. X gives magnetization to A, gives rise to cross peak A. Cross peaks are also 4 peaks in the square pattern, but the structure of diagonal and cross peaks are different. Diagonal peaks both are in phase doublets in both the dimensions. Cross peaks are anti-phase doublets in both the dimensions. This is what we understood. So we will go further now and see how we can utilize COSY in understanding many things. I will show you how do we identify different molecules, coupled partners or otherwise, using COSY. I consider an example of 2 molecules. There are 2 protons here, 2 protons here. All are completely different protons, different chemical shifts. There is no symmetry here, and this proton and this proton is different. This and this are different. When these 2 are coupled between themselves, I will say it is a AX spin system, weakly coupled. Chemical shifts are far away separated. This also 2 protons form weakly coupled 2 spins, gives rise to 4 peaks. 2 for A and 2 for X, 4 peaks we get. Here 2 for A and 2 for X, 4 peaks. So each molecule give 4 peaks, and this is the pattern we are going to get. Okay, and each molecule will have 2 chemical shifts. Now I mixed up. I have taken the mixture of this molecule both this I have taken together. Now each of them when it gives 4 peaks for this, 4 peaks for this, 2 chemical shifts, 2 chemical shifts. This is the spectrum I am going to get. Now our challenge is to identify which are the coupled partners. which are the 2 peaks coming from, or 4 peaks coming from 2 different protons of one molecule. The question is very clear. The challenge is to identify what are the 4 peaks pertaining to each molecule. 4 peaks, if I identify, I know the 2 chemical shifts. How do you identify that? Now, there are various possibilities. If I want to identify the coupled partners, one, whatever I have marked in red, these 4 peaks may belong to one molecule, 2 protons coupled, AX will give 4 peaks. 1 and 2 could be coupled partners. 3 and 4 could be coupled partners. There is a possibility. So, these are 1 and 2 correspond to one molecule, 2 orthoprotons of one molecule, and 3 and 4 correspond to 2 orthoprotons of other molecule, which I showed. This is one possibility. What are the other possibilities? There are other 2 possibilities. One is 1 and 3 could be coupled partner. These 4 peaks may coming from one molecule, and these 4 peaks may be coming from other molecule. That is also possible. So, 1 and 3 and 2 and 4 are coupled partners. 1 and 3 is coupled, gives rise to 4 peaks, and 2 and 4 are coupled, give rise to 4 peaks. Then what is the next possibility? 1 and 4 are coupled, that gives rise to 4-line pattern. 2 and 3 protons are coupled, that is also another coupled. So, there are 3 ways we can think of coupled partners in 2 molecules. I can get simply I get a spectrum like this. But if I have to make an assignment, I have to say these 2 peaks may correspond to one molecule, these 2 may correspond to another molecule, these 2 peaks may correspond to other molecules. How do I do that? Now I can utilize the COSY and understand and make the assignment very easy way. Look at this one. If I take this molecule, mixture of this molecule, and run a COSY spectrum, if I get a pattern like this is the COSY spectrum and this is the diagonal, then I would say 1 and 2 are coupled. Why? These 2 are coming from one molecule, because see, as I told you, 2 peaks, this will give 4 peaks, diagonal in a square pattern, in phase doublets, both this gives diagonal, x 1 and 2 both will give diagonal peaks, 4 peaks in phase diagonal, in phase doublets. And also 1 is coupled to 2 means there is a scalar coupling, 1 will give a cross peak to 2 at this frequency. 2 whose chemical shift is here gives rise to cross peak to 1. Remember, the peaks coming on the diagonal correspond to its chemical shift of the protons. Now, this is the chemical shift of this proton, this is the chemical shift of this proton. So, proton 2, if I go horizontally here, it gives a cross peak to 1 like this. Proton 1 come down here, go here, it gives a cross peak to 2. It tells me 1 and 2 are coupled, but it's from one molecule. 1 and 2 are giving cross peaks from one molecule. Look at the other one. There is another possibility. 3 and 4 can come like this and coupled. I will say these 2 are diagonal peaks, correspond to chemical shift of 3, chemical shift of 4. Now 3 and 4 giving a cross, 3 is giving a cross peak to 4, 4 is giving a cross peak to 3. That means 3 and 4 coupled. So there are 4 diagonals and we have cross peaks between 2 of them. These 2 cross peaks tells me they are coupled from one molecule. These 2 cross peaks tell me 1 and 2 are coupled and they are from another molecule. So if my question, I wanted to assign 4 peaks, my challenge was which are the coupled partners. If I simply run a COSY spectrum of this mixture, if I get a spectrum like this, then I immediately say these 2 are from one molecule and these 2 are from other molecules. All right, this is how it is. Spin 1 and 2 are coupled, spin 3 and 4 are coupled. Alternately, if I get a spectrum like this, very interesting. Now sit on this diagonal, come vertically down, go horizontally here, and you get a diagonal peak. The 2 diagonal peaks are there and they get cross peaks. You go along this axis, you get cross. So 1 and 3 gives rise to cross peak. 1 is giving cross peak to 3 here, 3 is giving cross peak to 1 here. It gives to 1 cross peak. So that means what I would say is if I go by this diagonal, if I write then what I say, 1 and 3 are coupled, because it is giving cross peak, and I have put one color. And another one is obviously left over 2 and 4 are also coupled. If I get a COSY spectrum like this for this mixture, then I will make the assignment of this doublet and this doublet for one molecule, this doublet and this doublet I will assign for other molecule. On the other hand, if I get a spectrum like this is another interesting thing. So now one come down, you get a cross peak, go horizontally here, you get a diagonal. So when these two, when the cross peaks go vertically up and horizontally, if you hit two diagonal peaks, then they are coupled. That is the assumption. That is understood. You have to understand that. So if one start with one diagonal, come horizontally, vertically, come horizontally, you meet another diagonal, and then this cross peaks tells me these two diagonal peaks are coupled. That means 1 and 4 are coupled. Exactly what I saw in the previous. Okay, 1 and 4, 1, 2, 1, 3 are coupled. Here 1 and 4 are coupled, and also 2 and 3 are coupled, because from 2 come vertically down, go horizontally here, there is a cross peak here between 1 and 2. 1 and 2 are the diagonal peaks, and when you go, you can complete a square going vertically down, going up, going horizontally, and then going up and going horizontally, you can complete a square. That means I will say spin 2 and 3 are also coupled. So there are 3 possibilities. Simply take a COSY spectrum, and looking at the COSY spectrum, you will say which protons are coupled, which 2 spins are coupled, and they are from which molecule. Easily you can do that. So we know how to use the COSY. Let us use the COSY for analysis of the spectra of simple molecules. We will analyze the COSY spectrum of simple molecules. We get a feel for what is happening. So with that we will become more familiar. I will start with a simple molecule, ethyl 2 butyrate. This is a molecular structure. I have written, see, 1, 2, 3, 4, 5 are the protons. Okay, proton A is here, proton B is here, and A and B are the two numbers I have given, but 1 is a CA3, 5 is a CA3. That is correct, because a terminal group. Always terminal group, as I have been telling you, comes at the high field. One of them correspond to one of the CA3. Whether this peak correspond to this CA3 or this peak correspond to this CA3, I do not know. I have to identify. How do I do that? What I am going to do is, simply I will sit on one of the diagonal, come vertically down, I hit a cross peak. Look at it. I come vertically down here, I am hitting a cross peak. When from here I hit a cross peak. Go horizontally, I get a diagonal. So these two diagonal peaks are there. That means this proton and this proton which comes on the diagonal are coupled. 4 and 5 are coupled. And afterward there is no other this thing, you can complete the square. That means this 4 proton, 4 and 5 are coupled. Any other coupling here there, you can't see it. It forms a closed coupled system, one spin system. So we can safely say this peak is because of CA3, and this one is because of CH2. We could easily say that. Next, what is the other thing we have to see? Other CA3. You will start with other CA3. This is another CA3, again terminal CA3. Come down, go horizontally, you complete a square. That means 1 is coupled to 2. Next one. Okay. At the same time, you can see 2 is also coupled to 3. You may ask me a question, why not this 3 and this, why not this 2? You can complete a square like this, and this may become, and this also may become, you may say this is 2 and this is 3. We can say that, but we can also use some multiplicity pattern. For example, this will be more complex, because it will be split into a quartet because of this, and further each of the quartet is split into triplet because of this. So, it is a more complex pattern, whereas this will only be a triplet because of CH2. So, sometimes you have to use your other idea of understanding of multiplicity pattern. See, this is more complex here than this one. I have not, it is not expanded. If you expand, you will see. That is why I would say this will complete a square. This is proton 2. Now, from the proton 2, you can do one more thing. Go horizontally up, go horizontal and go vertically up. You see it another peak here. So, 2 is coupled to 3. As a consequence, these two are coupled and giving rise to cross peak here. This cross peak correspond to 1 and 2, whereas this cross peak correspond to 2 and 3. There is also A is also this one. This A3 is also coupled to 3. See, all the 3 is there. You can see the cross peak here. Cross peak is there from here to here to here. There is, this is coupled to this is also coupled to this. There is a long range correlation. It shows correlation to both the protons. So, what you understand from this is 1 is coupled to 2, gives a cross peak, and 2 is coupled to 3 and that gives a cross peak. So, you can make the assignment of all of them. Very easily you can make the assignment. Go to a little bigger molecule. Instead of butane, we will go to heptanane. This is 3-heptanon. This is the COSY spectrum. Now, where do we start with to assign? As always, start with a one where you are confident of assignment. I would say these two CH3s come at the high field. True. And then both of them are triplets. Why? CH3 is coupled to CH2, this CH3 is coupled to CH2. So, both the CH3s are triplets. So, obviously, we can see both are triplets here. So, I can start with one of them. I do not know which is which. We will make an assignment. So, what we will do is we will start with one of the peak. Otherwise, we can also do one more thing. We can also start with the, we have to use the other way, these two CH2s. So, we can start with that CH2 and do the assignment. That is also, these two, the reason is these two should be downfield because it is directly within C double bond O. That is one way, but I would even go like this with the CH3. It does not matter, this is how it is chosen here. So, go with one of the protons, come up, come here, you see, horizontally and go up and complete the square. If this is proton 2, let us say if this is proton 2 and if this is coupled to proton 1 and it completes a square. Look at it, it is not coupled to anything else. This forms one square, right? But if you carefully see, there is only, this is the only two coupled partners, nothing else. Of course, you may say there is a peak here, but they are not same. It is there are two peaks overlapped here. It is from other proton, but this forms a complete square. So, I would say if this is one of the protons CH3, this has to be 2 and this is the only isolated partner here. You cannot see anything else here apart from this. These are the only, these two groups are isolated coupled partners. Then obviously, there is another peak here. I can start with CH3, come down, complete the square. If this is another proton CH3, then this complete a square. This has to be the next immediate coupled partner. I would say this is proton 6 because it is the immediate coupled partner. What will happen? This 6 will further couple to say 5. From 6 you come down, complete the square now. Then what are you going to see? This 6 is coupled to 5. So, this has to be 5. I can say this is 5. Started with for example 7, I got a square. So, immediate coupled partner for this is 6 and from the 6 diagonal I completed a square, then I know this is 5, this one. Further what I am going to do? I will start with 5, come down and complete the square. That means this has to be 4. So, 4, 5, 6, 7 forms one spin system. Start with 4, go here 5, go with 6 and then meet 7. So step by step in a like a ladder, you can go and make the assignment. So here in this molecule, there are two groups of coupled spin system. One is this group, other is this group. Both we could make the assignment just by looking at the COSY cross peaks. All you have to do is sit on a diagonal on one of the peaks in which you are confident of your assignment. With that, start coming down, go up horizontally. If you hit another diagonal, that means these two peaks are coupled and you should complete a square. From that diagonal, you can continue like this further. See whether there is one more square, and then from other one. So like you can keep on extending like a ladder, one after the other, like here. So like start with this, go here, here, like this. Keep going one by one. And then complete assignment of all the coupled partners can be made. Okay. Now we will go to the bigger molecule. Slightly, I am increasing the complexity as the time goes by. We will analyze the spectrum of aniline molecule. This has a symmetry here. Here, if you carefully look at the structure of the molecule, you can immediately say these phenyl protons, there is a symmetry, of course there are only two protons, they form an isolated spin system, obviously, and it is not coupled to anything else. They are far away separated, it is not coupled to anything else. So obviously that is one spin system. Next, if I want to start the assignment, okay, that is this one. I can go ahead and make the assignment here. This forms a phenyl group. One complete spin system can be assigned, alpha and beta aromatic protons. But further what happens? If you look at it carefully, this molecular structure, you will see A and F are the protons which can split only by a single neighbor. This can become a doublet because of this can become a doublet because of this. And 1, 2, 3, 4 bond couplings are not there, let us say. It is not there. So this is also 4 bond coupling is not there. This A and F are the only protons which can be a doublet. It has to be doublet because it is split by only a single proton. So with that, I have to identify two doublets here. Where are the two doublets here? In the isolate in this group, there is one doublet here, carefully I can see. There is another doublet here, I can see. Both are there. Of course, very clear doublets. Fine. One important thing you should also carefully observe, A has a trans coupling with B. E and F are cis coupling. Remember I told you already long back. Trans coupling is always larger than cis coupling. This could be about 12 to 15 hertz. This could be about 7 to 10 hertz. So trans coupling being larger, coupling between A and B proton, that means this is larger. So I would start with a proton A, which is a doublet with a larger separation. I can see here there is a proton with a larger A. Look at this doublet, this is smaller than this. Obviously, this is a cis proton which has a cis coupling. I would carefully say this is A and this is F. I can even make the assignment. All right, we will start with that. Start with now A. Come down here, you hit a peak. Go horizontally, you hit a diagonal. That means A is coupled to B, it's somewhere here. So it completes a square. If this is A, this has to be B. All right, I know B. From B, I can go further up, complete this square. So that means B is coupled to C, this is C. Now with C, I can go like this. I can complete this. C, I can complete a square, this is D. From D, there is another coupling from D to E. So you can, if you carefully see from D, one peak is coming here. There is a diagonal. I will erase this thing to make it clear. So from D, it is coming here and you see a diagonal here. Go vertically up and complete that. That means this has to be E. Further, from E diagonal, you are going to have coupling with F like this. This is a diagonal. So A and E and F are coupled. So, very easily you can make the assignment. Start with the known one. From I will repeat it quickly, you can understand now. A to B is coupling. Okay, I will remove the markings first. Okay. A is coupled to B and forms a square. From B it forms a square, that is C. Then C it goes to D. From D it comes to E. From E we are going to get F, and this is a aromatic group. Very easily we can assign all the peaks by using the COSY spectrum of aniline. We will go to another bigger molecule, little lengthier. Now we will make the assignment. Where do we start with? As always, look at the molecule carefully. Both these molecules will have terminal groups which are CH3, and each of the CH3 is coupled, next immediate neighbor is CH2. Obviously, these two peaks have to be triplets. There are two triplets here. So, we will start with one of the triplet and then start making the assignment. Now, you know how do you go. First sit on the diagonal with one of the peaks and then complete a square like this. So, this CH3 you come down horizontally, vertically, go horizontally and complete the square, and there is no other coupling, no other cross peak between these two. That means this and this are coupled partners. If this is proton 7, this is proton 6. What is the next one? Next one, of course, I can see one more thing here, and this forms another pair because this is another triplet. So, where is, if that is the triplet, what else it should be? This has to be 1 and this is 2. It starts with this. You see, look at this. It starts with this. This complete the square. 1 come down horizontally, complete, and this there is a cross peak. So, that means this and this are coupled. So, this has to be 1 because we already assigned 7. This one. This and this have been assigned. So, this has to be proton 1. So, when you complete this square, this is proton 2. You understand? So, we have assigned proton 1 and 2. Obviously, next leftover is this group. This is 2 CH2s. One which is attached to oxygen directly will come down. So, I would say that is proton H3, and proton 3 sit on the diagonal and then go horizontally and vertically like this, will complete a square. So, that means if this is 3, this has to be 4. This is 3, this is 4. That means this COSY spectrum identified 3 groups of coupled spin systems in this molecule. Molecule looks little lengthier, bigger, but if you know how to assign the COSY spectrum, it is a matter of 5 minutes. We can assign all the peaks. Simply you have to sit on one diagonal where you have a confidence is there in your peak, complete the square, and if you hit another diagonal, these two diagonal peaks, chemical shifts, if you know those two are the coupled partners, then you can keep extending the logic in a stepwise manner. We will go to the little bigger molecule, bit more complex. How do we assign this one? This is a spectrum of trans 2 cis 6 non-diagonal. Again, if you carefully see, this is CH3 I have to start with. It is a triplet. So, I will start with that. Okay. And then if you come down, there is no other cross peak, only this, and go horizontally and complete the square. So, if this is CH3, then this has to be CH2. I would say H8. Easily I can make the assignment for that. What next? Come from 8. See, there is a cross peak here. If you carefully see, there is a cross peak there. Complete this. Go horizontally, complete this square. So, I have completed that square. So, then what is the other one? It has to be 7. And then next with 7, there is also coupling with something else. They are unresolved here. If you look at carefully, here there are 2 peaks overlapped, unresolved. As a consequence, 6 is also there. There is a cross peak between 6 and 7, but because of poor resolution, we are not able to see that. All right. With 6, I can go further, complete the square, that has to be 5. Afterwards 6, it has to be 5. Then 5 has a cross peak coupled to 4. This has a cross peak here, and these two are not resolved. Again, it is poor. You can carefully see there is no resolution at all here. There are two peaks overlapped here, and you are not going to see here. So, as a consequence, you do not see it, but there are peaks here. So, that must be 4. 5 is coupled to 4. What next? 4 if you complete, it is coupled to 3. I complete the square, and from 3 I can sit on the diagonal of 3, go another, complete another square, then this has to be 2. From the 2 diagonal I sit, come down and complete this square, then obviously that has to be 1. So, molecule looks fairly complex, but if you know how to analyze the COSY spectrum, very easily you can make assignment of all the peaks without any difficulty. Let us look at this molecule, bit more complex, lengthy molecule, but I tell you it does not take much time at all to analyze. Obviously, these two are the isolated group. This is CA3, and there is a one more quartet. Where is the quartet we can think of? Only this. So, this is 7, this is 6. I am sorry, 8 here. The remaining things are here, and of course, this is a bromine which is attached to bromine. It comes downfield. This is 1, and it has to be triplet because it is coupled to only one of them. And all other things, this is coupled to 2 CH2s, some complex multiplicity pattern. This is coupled to 2 CH2 complex multiplicity pattern. This is coupled to 2 CH2s complex multiplicity pattern. But only this CH2 has coupled to this and is a triplet. Very easily we can make the assignment of all these things. Even I do not need a COSY, but nevertheless we will use the COSY and then make the simplest assignment for this thing. Okay? I can assign all those things. We will go to COSY now. In the case of COSY, start with 8, come here and complete this. Here the problem is to assign 2, 3 and 4, which is 3, which is 2 and which is 4 we do not know, because each of them are coupled to 2 CH2s. On either side there are CH2 groups. So, which identical multiplicity pattern is there, which is 2, which is 3, which is 4 you do not know. For that COSY helps you. Start with proton CH3 at high field 8, you complete a square, it becomes this is 7 and 8, and then this is 1 because downfield CH2 I know that, complete this square, then this has to be 2. I know, we carefully without any confusion I can assign what is 2, and from 2 I can go like this and complete this, then that is 3. See, in the 1D there was a confusion, multiplicity pattern was identical, I do not know which is 3, which is 2, which is 4. So, there is a now I can reason out by just looking at the cross peak in the COSY, and this is obviously 3 is coupled to 4 here, and that is 4, and 4 complete this and forms a 5. Everything can be assigned, and this is the pattern here. So, like this we can start assigning this thing, and lot more things we can do, and few more example of complex molecules, especially biomolecules I will take to make you more comfortable. COSY is the one thing which everybody uses. If you are a scientist using NMR spectroscopy, you cannot do away with COSY to make you more comfortable, because this course is specially designed for the analysis of the spectra. In the next class I will take few more examples to make you understand COSY, and then we will go to few other example types of COSY experiments, what type of COSY we have and everything later. So, I am going to stop here. Today we discussed, it took several examples of analysis of the COSY spectra, starting with the 2 molecules, and then if you take the mixture, how the pattern comes like that. Then the real examples of COSY spectra of several simple molecules to little bigger molecules we took, and we know how to analyze. All you have to do is simply identify one of the peak in which you are confident of assignment, sit on a diagonal of that, come down, see the cross peak, you should complete the square, so that cross peaks should be in pairs, and then from that diagonal go to another cross peak if is there, complete that square. From that diagonal continue like this. You can go one by one like a ladder, and then make assignment for all the protons in a given molecule. So, with this I am going to stop. We will continue with the other things in the next class. Thank you very much.